Welcome to today's episode, where we're diving into the intricate world of distributed transactions. As systems expand and grow more complex, managing transactions across multiple nodes can become quite the challenge. Today, we'll explore a fascinating strategy known as coordination avoidance, along with the innovative read atomic multi-partition or RAMP transactions. These concepts are really shaking things up in the realm of distributed databases. So let's start by unpacking coordination avoidance. At its core, this is all about managing state across various nodes in a distributed system. While coordination is often necessary to maintain consistency, it can also introduce significant overhead, which can hinder performance. Coordination avoidance, on the other hand, allows operations to be executed independently. This independence can significantly boost both scalability and efficiency. Now, to keep everything running smoothly across distributed systems, we need something called a merge function. This function is key because it reconciles updates made independently on different nodes, ensuring that diverged states can converge seamlessly. For a system to effectively implement coordination avoidance, it must meet several important criteria. These include consistently satisfying necessary invariants, allowing transactions to either commit or abort based on their state, and enabling nodes to maintain independent states while still being able to converge when needed. In a distributed environment, transactions can often execute locally without needing to coordinate with other nodes, unless they require state from different partitions. When a transaction commits, the changes made to the local snapshot are then migrated and merged with the snapshots of other nodes. This independence in local execution is crucial, as it allows multiple transactions to proceed concurrently, enhancing overall throughput. One standout approach to achieving coordination avoidance is through RAMP transactions. RAMP employs multi-version concurrency control and utilizes metadata from ongoing operations to fetch any missing state updates from other nodes. This clever strategy allows read and write operations to happen simultaneously, which significantly cuts down on the need for locks and boosts performance. Now, let's talk about the two essential properties that RAMP introduces: synchronization independence and partition independence. Synchronization independence means that one client's transactions won't block or interfere with another client's transactions. Meanwhile, partition independence allows clients to operate without needing to reach out to partitions that aren't relevant to their transactions. RAMP also establishes a read atomic isolation level. This means that transactions can't see any in-process changes from uncommitted or aborted transactions. Essentially, a transaction either sees all updates or none at all, effectively preventing those frustrating fracture reads where a transaction only observes a portion of the changes. One of the most impressive features of RAMP is its ability to provide atomic write visibility without the need for mutual exclusion. This is a significant advantage over traditional lock-based methods, as it allows transactions to proceed without stalling one another. By distributing transaction metadata, RAMP enables reads to detect concurrent writes, ensuring that transactions can access the latest record version seamlessly. To maintain that read atomic isolation level while permitting concurrent operations, RAMP employs a two-phase commit process. In the first phase, it prepares the writes and places them in their respective target partitions without making them visible just yet. The second phase either commits these changes, making them visible atomically across all partitions, or rolls them back if necessary. This mechanism ensures that all nodes see the same state changes at the same time, preserving the integrity of the transaction across the distributed system. Plus, it allows multiple versions of the same record to coexist, which is essential for handling in-progress read requests. Once all concurrent readers finish, any stale versions can be discarded, optimizing both storage and performance. However, despite these advancements with coordination avoidance and ramp, achieving performant and scalable distributed transactions still presents challenges. The overhead associated with managing conflicts and ensuring consistency can be quite significant, especially as systems grow larger and more complex. The strategies we've discussed aim to minimize coordination, using invariants to determine when it's necessary and when it can be bypassed. As we explore distributed transactions, it's also worth mentioning atomic commitment algorithms like the two-phase commit, 2PC, and three-phase commit, 3PC. While these algorithms are relatively straightforward to implement, they do come with their own limitations. For example, 2PC requires a coordinator to be available throughout the commitment process, which can reduce overall system availability. On the flip side, 3PC addresses some of these issues but still faces vulnerabilities during network partitions, often leading to split-brain scenarios. Looking ahead in the realm of distributed transactions, consensus algorithms are becoming increasingly important. Algorithms like Paxos offer enhanced fault tolerance and decouple decision-making from their initiators, allowing participants to agree on a value rather than just deciding whether to accept a proposed one. Although consensus algorithms are more complex than atomic commit algorithms, their benefits in terms of reliability and scalability make them an appealing choice for modern distributed systems. In future episodes, we'll dive deeper into these consensus algorithms and explore their implications for distributed transactions. To wrap up, the landscape of distributed transactions is evolving rapidly, with coordination avoidance and innovative approaches like ramp leading the charge. By enabling transactions to execute independently while still maintaining consistency across nodes, we can greatly enhance both performance and scalability. As we continue to explore these concepts, we'll uncover even more strategies and technologies that are shaping the future of distributed databases. Thanks for tuning in today, and we can't wait to dive into more exciting topics in our next episode.